Venuganti will be presenting this, and I'm sure you find this as exciting and as interesting as I did when I read that. So, over to you. Oh, are you leaving? Okay.
Hello. Yeah, so if you wanted more speakers for this, I think you should have accepted more papers.
How many have you accepted?
Hello everyone, my name is Sumedh. I'm a graduate student at the University of Illinois at Urbana-Champaign. Happy 4/8 or 8/4, depending on what part of the world you're in. Today I'm going to be talking about my work that I did with Dr. Nicholas Bhatti, advancing math formula search using diverse structural and semantic representations. Okay, so we have mature search engines for things like text with Google, or for whatever reason if you use Bing. We have TinEye, which was a really good image search engine, and Shazam for Spotify, which got integrated into Snapchat, where if you hear a song, you click, it'll find the song title for you. However, for math, when I tried typing it in this morning, these are the results that I got. But for math search engines, they're not as performant or as strong as search engines that are established for known media like text and sound. So our goal was to improve the performance on these mathematical queries. So here's one sample task. A user enters a query, and your goal is to retrieve formula that are similar to the query, and documents that are similar to the query as well. Another common use case for this that we'll often see is on Map Stack Exchange or forums, where users will enter queries that contain both formula and text, and the text matching happens really well, but if the formula starts to get complex, you may not get great results. Other applications for this include RAG, where if someone asks a question about a formula, you may want more formula-specific search. So, to begin, before we started developing our engine, we took a look at a bunch of past math search engines submitted to math search competitions. And we learned some lessons from those submitted competitions. One, text-based indexing alone is insufficient. You can look over here and we see these two equations, a squared plus b squared equals c squared, and you look at x squared plus y squared equals r squared, and the meaning of both of these equations is the same, but they look very visually different. So if you were to use a string matching algorithm, you may not get the best results. Another thing is formula variability. So you look over here, these two both represent derivatives, but they may not be the most lexically aligned on the left-hand side. So even in early search engine competitions that existed, teams that used just text to match performed quite poorly. As search engine competitions evolved, what we noticed is that lots of teams started using tree-based features. So MathML was developed originally to help equations render properly in browsers, and to make sure that they display properly. So XML inherently has this tree-like structure, so what people started to do is start leveraging paths from the root to the leaves of these mathematical equations, and extract features from the trees from these paths. So that gives you a bit more information about, let's say, how equals and I are related, as opposed to just looking at a simple set ordered from left to right. Moreover, when people started making neural embedding models to find similar equations, they found that even complex neural embedding models, when augmented with tree-based features, outperformed just neural embedding models alone. Sorry. And then finally, a lot of these teams in these competitions used Lucene as their backend because they needed rapid indexing, they needed inverted indexing, they needed fielded query, they needed to be able to assign custom scoring functions to things. So a lot of the successful teams, instead of trying to reinvent the search engine from the bottom up, leveraged existing libraries that supported the functionalities they needed for good math search engines. So with that, I'm going to present our new search engine and the indexing process. So we start with the corpus of documents. From the corpus, we extract a bunch of formulas from the documents. For every document, we are given three representations. Two of these are XML representations at the top. One of the XML representations captures the structure. The other XML representation focuses on how the symbols are laid out spatially. So there's an operator relationship that one of them captures, and that's content ML. And there's a symbolic relationship that the other one captures, and that's presentation ML. And latex, we all use. So we get these three representations of the formula, then we convert them into an operator tree. So we take the content ML, and we make trees like this that represent the equation above. Then we extract the leaf, we go from leaf to leaf, and we extract all pairs of leaf to leaf paths to form a feature set that consists of the relationships between the leaf nodes. Finally, we index this information into a graph database so that given a feature, you can look up an equation, and given an equation, you can look up all of the features. So, there's three key differences from the past that we found, that we first did. Variable rewriting ability. So in Passport, people often would use really hyper-selective leaf names. So even if they tried to bucket like variables, they would have 12 different categories. In other Passport, they use really broad labels at the bottom of the for the canonicalization. So maybe they would just say document level equation or paragraph level equation. They would not have granularity. So we saw hyperspecificity in the leaf nodes, and at the same time we saw approaches that took really broad approaches. For example, X and Y are both variables. So we decided to use three: variable, ASCII, and variable, ASCII, and num. That's it. We used three to kind of standardize the leaf nodes. So that's one difference. The second thing is this leaf-to-leaf shortest path. In past works, as I showed on the previous slide, people would use root-to-leaf features. In further works, people started creating embeddings that omitted root-to-leaf features, but still used other structural components. This taught us that root information is relevant sometimes, but other times it needs to be omitted. So when you take the leaf-to-leaf shortest path, some paths naturally omit the root node, and other paths include the root node. So that kind of, we believe, naturally balances the relevance of root information. And finally, we used a GraphIR backend, and all of the other engines you will see. The only reason this was done is that there's no inherent capability that this GraphIR model provides that you can't use a standard database for, but it allows us to visualize the interconnectedness of these equations. So, retrieval. We start again with the three representations of the formula. We convert the formula from content ML into a map operator tree in the same way, and we extract the features leaf-to-leaf shortest path in the same way. Next, we make a query to our graph database, and we find, hey, what are all of the equations that contain each one of these features, and what are all of their features? From this, we calculate a feature similarity score. Next, we get the equivalent latex representations of the retrieved formula. We compute a similarity score between the retrieved latex formula and the original latex formula and get a latex score. Finally, we use the presentation ML representation to extract a symbol set consisting of symbols from left to right as if you were reading them in the equation, and calculate a symbol set similarity score. We weight them and combine them, and that's how we rank the similarity between the query and a formula. Okay, so we talked about three components of ranking. Why did we rank feature similarity this way? Well, you can imagine two equations, one that shares two features. You can have a query and a formula that share two features, but one of the formulas has 1,000. And you can imagine a query and a formula that share two features, but the response has 3 features total. Obviously, the one with 3 features is more similar. So we want to balance the proportional relevance of the features by taking the intersection of the union. For latex, we know that edit distance, or the minimum number of edits to align things, is a measure of distance. So we took the inverse of it to get a similarity score. Next, for symbol sets, when you make symbol sets going from left to right in the equation, you want something that measures the overlap between the symbols, but also allows symbols to be reordered but not penalize them too much. So we chose a similarity method that has transpositions in it. And finally, we weight them and combine them to get the rank between the query and the retrieve formula. Real quick, these are the ECIR results on this data set. So what we notice is L2L, system over here, performs well in exact matches. But if you look over here on the top row, the red circle and the green circle, we see some deficits. Okay, let's take a look at the RQ3 results. So if we look over here on this data set, we have two boxes that we outperform on, but we don't perform so well, or we perform well, but only 0.008 delta from the best performances. So why does this happen? We took the two weights, we fixed W symbol and varied W feature and W latex and made a heat map. And what we see is that as you move in from the corners of the heat map, you get a maximum around the center. What this means is that even though we vary from 0.616 to 0.688, that's only a 7.2% variation. So it's the inclusion of the feature spaces instead of the coordinated unit weight connected parameters that gives us the score. Next, we did an experiment where we suppressed different components of the ranking function. So we set one weight to 0, and then looked at the data, and then another weight to 0, and we looked at the data. And if you look at this, different queries performance drop differently when different components of the feature space are suppressed. What this tells us is that all three representations are needed to get good results. Finally, we did a qualitative analysis of the queries that were most impacted by suppressing feature space. Just checking out one of them, the feature rank. So when we turn up the feature rank and try to do a comparison, you'll notice things like the implicit multiplication between these two are missed in the text representation, but they exist in the tree-based representation. Over here, these special symbols A and Rn in the symbol rank, well, when we did the operator tree standardization, they both became masking, so there was no difference between them. So they relied on a degraded version of the formula. And here, the concepts of covariance and correlation are similar, but they have different meanings. So that latex string matching is essentially capture these subtle differences. So thank you, everybody. If you're interested in our work, please go to mldgroup.xyz. You can reach me here, and I'm happy to hear.
Hi, thank you for your presentation. So if I'm not mistaken, in Champaign-Urbana, there's Mathematica and Wolfram research? So they have some sort of query language to go from natural expressions to a mathematical function. Is that an application you've looked at for this research? So say, using natural language to retrieve formula?
Yeah, so that's another line of research, and the competitions that I looked at or took the data sets from also have tasks that have natural language and equations in them. For this, I wanted to focus on just the formula retrieval aspect of it. I also think that Wolfram, and have you heard of Symbolab? Okay, it's what I used to cheat on my homework in high school. But if you enter like equations even slightly incorrectly, it's sort of restrictive in the way that you need to put in the input format. So I think the problem of mapping natural language to specific equations is separate. But this potentially could be used to find similar measures.
Okay, thank you.
Can I just ask a related question? Because one of the things that I noticed was, do you have a feel for how commonly people ask questions like that? So you mentioned Stack Overflow, I think.
Yeah.
And compared to more like conceptual questions. So for me, it was a bit of an analogy with image search. Mm-hmm. So when I search for images, typically people say, I'm looking for the bar that serves good beer for me. I'm just completely made up. Rather than having an image of something and then give me more of this. And I thought if I search for, let's say, things like zip flow, power law distribution, rather than the actual formula. So do you have a feel for how common one or the other? Because I imagine that the natural language.
I imagine that the conceptual search is probably way more. I don't have data to prove it, but I think we can all naturally agree that the conceptual search is probably a lot more important. I think that this starts to become relevant when you look at sometimes equations that are similar in structure but appear in different fields. If we sort of propagate this up to a document,